Some modern language models have an absurd number of total parameters, but they do not necessarily use all of them for every token. That is the key idea behind mixture of experts. Make the model huge, but activate only a small part of it at each step. A dense transformer uses almost the same full set of weights for every token. A sparse mixture of experts model keeps many expert networks, but a router selects only a few experts per token. Total capacity goes up, while active compute can stay much lower. In most transformer language models, MO usually replaces the feed-forward network, not the attention mechanism. Attention still moves information between tokens. The MO layer transforms each token through selected expert MLPs. An expert is usually just a feed-forward network with its own parameters. It is not a separate chatbot, and it is not a handwritten skill module. During training, different experts learn different useful transformations because the router sends them different token distributions. The router is a small learned network. For each token representation, it produces routing logits over all experts. After a softmax, those logits become scores saying which experts should process that token. Most sparse MOE layers use top K routing. Instead of sending a token to every expert, the router keeps only the best 1, 2, or a small number of experts. The selected expert outputs are then combined using the router weights. The core formula is simple. The MO output for a token is the weighted sum of selected expert outputs. The weights come from the router, and the experts are ordinary neural networks applied to the token. Routing usually happens per token, not per whole sentence. In one sequence, code-like tokens may go to one expert, punctuation to another, and natural language tokens to others. This is why MOE is a conditional computation system. A naive router can collapse. If it sends almost every token to the same expert, that expert becomes overloaded while the others barely learn. Then the model loses the whole point of having many experts. To prevent collapse, MOE training often adds a load balancing objective. The exact formula varies, but the goal is consistent. Encourage token traffic to be spread across experts while still letting the router choose useful experts. There is also a systems constraint called expert capacity. Each expert can process only a limited number of tokens in a batch. If too many tokens choose the same expert, the implementation may drop, reroute, or pad tokens depending on the design. During training, gradients update both sides of the system. The selected experts learn to transform tokens better, and the router learns which experts should receive which tokens. This creates a moving target, which is powerful but harder to stabilize than a dense MLP. People often imagine experts as clean categories like math expert, code expert, or grammar expert. Sometimes partial specialization appears, but real experts are messier. They specialize in patterns of activations, not neat human labels. This gives MOE its famous scaling trade-off. Total parameters can be very large, giving the model more memory and capacity, but the active parameters per token can be much smaller, because only selected experts run for each token. The hard part is systems engineering. Experts may live on different GPUs. Tokens must be dispatched to the right devices and then gathered back. This all-to-all communication can become a major bottleneck. At inference time, MOE can reduce compute per token, but it does not automatically make everything cheap. You still need to store all expert weights somewhere, route tokens efficiently, batch requests well, and avoid communication dominating the speed-up. MO has real failure modes: routing collapse, expert undertraining, drop tokens, unstable auxiliary losses, poor batching, and latency spikes from communication. It is a scaling technique, but it is not a free lunch. Modern MOE designs add many refinements: shared experts, routed experts, fine-grained experts, expert parallelism, capacity control, router regularization, and sometimes dense layers mixed with sparse layers. The core idea remains conditional computation. If you remember one thing, remember this: MOE separates total capacity from active compute. A router chooses a small subset of expert MLPs for each token, and the system must balance quality, load, memory, and communication.